It was my first time in El Paso. The occasion was a business trip to White Sands Missile Range, an element of the Test and Evaluation Command of the Army Materiel Command, some 40 miles to the north. Just as promised, a White Sands car was waiting for me. Although it was January, the day was warm and sunny. On our way out of town, I noticed a number of motels. I was interested, since I'd have to check into one that night. As we headed north into the desert, I thought of the assignment which had brought me here. As an engineer in missile research and development, it was my job to investigate a new White Sands facility for nuclear effects testing of weapon systems. In less than an hour, we arrived at the missile range. It turned out that my destination, the nuclear effects branch, was only a little way down the road from the guard gate. The White Sands people were expecting me, and in almost no time, I joined a group being briefed on purposes and capabilities of the nuclear effects branch. I learned that though operated by the Army, branch services are available to all government agencies and their contractors. These services are primarily to provide nuclear environments closely approaching those produced by detonation of nuclear weapons. In these controlled environments, branch facilities make possible the study of nuclear effects on both individual components and complete weapon systems. The branch's two particle accelerators and its fast burst reactor are primarily engineering tools. It is the only Defense Department facility providing the three major radiation environments and the instrumentation peculiar to testing nuclear effects upon weapon systems. The briefing over, we took a tour of branch facilities. Before entering the operational area, you are issued two film badges, one for detection of neutrons, the other for gamma beta radiation. First, we took a look at the vault for storage of radioactive sources. "18 inches of glass provides safe observation. Next, we visited personnel of the health physics section, who continuously use various radiation measuring devices to monitor the radiation exposure of employees and users. Then we toured the dosimetry section. Here are the most modern of devices for measuring and analyzing radiation received by test items. Dosimetry equipment includes a 400-channel pulse height analyzer, a glass rod microdosimetry system, a lithium fluoride thermoluminescent dosimetry system, fission and threshold foil counting systems with automatic sample changers, a film dosimetry system, an automatic sample changing beta counting system with automatic data printout system, and a variety of calibration sources. A large security vault is provided for safeguarding classified equipment. Ample space is available to using agencies for such purposes as on-site equipment modification, engineering, administration, and preparation of material and equipment for nuclear effects testing. Outside space is provided for parking instrumentation vans. 6-inch conduits afford access to facilities inside for calibration and checkout of instruments prior to test. In this high bay area, instrumentation vans can be brought inside for monitoring and recording the performance of components being exposed to a nuclear environment. One such nuclear environment is provided by this linear electron accelerator. This device emits a stream of electrons, essentially at the velocity of light. When the electrons strike a heavy metal target, usually tungsten or lead, gamma rays are produced. Here preparations are made for a test in the linear accelerator exposure chamber. This item, a missile component, will be subjected to a dose rate of 10 to the 9th power roentgens per second. At this console, the accelerator is operated in either single pulse mode or at 10 pulses per second. The pulse width is continuously variable between 20 nanoseconds and 10 microseconds. The 20 nanosecond minimum pulse width assures good reproduction of the fission weapon gamma spike. The test item has been energized, just as it would be during an actual missile flight. Preparations completed, the technician makes sure the area is cleared of personnel. A press of the button seals the radiation exposure chamber. In the instrumentation room, performance of the missile component will be recorded. The accelerator is actuated and the test is underway. Experience has shown that some of the perturbations produced by the gamma spike are of sufficient duration to cause loss of control of a missile. This test is typical of those conducted to determine transient radiation effects on electronics. This is the branch's pulsed neutron generator. This device reproduces the high-energy 14.2 MeV neutron spike obtained from a fusion-type weapon. Ten to the 9th power neutrons are produced per 10 microsecond pulse. Here, a branch technician is preparing a transistor for exposure to the neutron bombardment of the generator. Placed in a test circuit, the transistor is proved to be in good working condition with a curve tracer. Now the transistor is positioned for exposure to the neutron environment. At the control console, the generator is put into operation. The transistor's performance during exposure is precisely recorded. The test over, the transistor is removed from the radiation cell and once again observed on the curve tracer. The scope pattern indicates permanent nuclear damage. In other words, atoms have been knocked from the transistor's carefully arranged atomic lattice. More than a half-mile back from the road is the fast burst reactor facility. Here we check in at the guardhouse. Stringent controls are exercised for personnel entering the area. An elaborate alarm system and the use of guards during tests assure maximum safety. Inside, we entered this 50-foot square room called the reactor cell. A complete missile system was being readied for nuclear effects testing. Dosimeters were placed for documentation of the exact radiation environment to be received. A 1-foot thick lead door shields the reactor, which is stored in a 38-foot deep pit after a burst. Here's a close look at the reactor without safety shield. A critical assembly fueled with uranium molybdenum alloy. It is capable of producing both high-yield, short-duration bursts and steady-state operations up to 10 kilowatts of power. Test items have been properly positioned for subjection to neutron and gamma radiation, simulating a nuclear weapon environment. The neutron spectrum of the fast burst reactor is a slightly degraded fission spectrum. The ratio of neutron dose to gamma dose is approximately 10 to 1. Using agencies may position their own instrumentation vans here, or vans like these can be provided by the branch for monitoring and recording experimental data. Cable conduits are available at all test locations, inside and out. Cable lengths needed are less than 100 feet to minimize spurious signals and potential drops. I also noted that electrical power outlets and high-pressure air sources are plentiful. Soon this particular test will begin. In the reactor cell, the missile system is actuated. In the control building, shielded by 24 feet of earth and concrete, the fast-burst reactor is operated. Highly precise instruments are set to record performance data on both the reactor and the equipment under test. Everything in readiness, the reactor is energized, and 10 to the 14th power neutrons per square centimeter at the surface of the safety shield achieved. The reactor burst width at half maximum power is 45 microseconds. The reactor's temperature rise during the burst is around 250 degrees centigrade. After burst, the reactor emits an intense gamma radiation for a relatively short time. However, to allow almost immediate access into the cell, the reactor is lowered into the pit and the lead shield moved over to cover it. Soon the engineers conducting the experiment can safely enter the cell. Dosimeters are collected immediately so that lab analysis may reveal as rapidly as possible the exact levels of radiation received. For larger test items, or to obtain wider dispersion of such items, the reactor can be placed outside, on top of the cell. It is moved with an ordinary forklift truck. At the end of the tour, I was thinking of the ways in which the nuclear effects branch could serve the needs of my own agency. For one thing, nuclear effects tests performed here could determine the necessity for circuit redesign and substitution of harder components. They could also establish damage thresholds needed in formulating tactical doctrine, such as salvo intervals. And the general fund of information collected by the branch on transient effects in carrying out investigations for the Department of Defense, including the Defense Atomic Support Agency, will be of real value for weapons systems design. As I said goodbye to the very capable White Sands personnel, I felt that my visit had been well worthwhile in ascertaining at first hand the capabilities of the United States Army's Nuclear Effects Facility at White Sands Missile Range, the only facility in the Defense Department providing all three major transient radiation environments in furthering the defense of the free world.